Okay, my friend, now I think you have a very good understanding of what is a pointer. Basically, it's just an address of a variable inside your RAM, inside your memory. Now we enter a little bit in murky area. Indeed, we have to understand what is this correlation between array and pointers. This, in my opinion, is the trickiest part related to pointers. So let's start from this definition. The name of an array is a synonym for the location of the first element. So basically the name of the array is an alias. So to a programmer, an array identifier is almost, and this almost is very big, just a pointer, because in most cases, arrays decay into pointers. Decay is a fancy word that means loss of type and loss of dimension. And yeah, I know, my friend, tricky, but I'm gonna try to make all of this as easy vanilla as possible. So what we're going to do now, we're going to create a program that is going to be self-explanatory about this dance between array and pointers. So the usual boilerplates, so include standard input output, and then as usual my main function, so int main. Okay, you perfectly know that to create an array you just do that, right? You just say, for example, let's pretend we have an array of integers. We say int array, which is the name identifier of the array, and you can say 10. So this is gonna create an object of 10 integers inside your RAM, more precisely inside your main stack frame. Now, I told you that at the end of the day, the name of the array identifier, is basically a pointer to the first element. If I do something like that, printf p new line, and I say r, I'm gonna get the address of the first element. So to make the proof, I can say p is equal to p, and I use here the address of array, the first element, array 0. Do you agree? This is the same, right? This is equal to this. Let's try to launch this program. So I'm gonna compile array pointer, and then I'm gonna launch. As you can see, there are two addresses and they are equal. So the name of the array is this one, and this is the address of the first element. So you can see that they are exactly the same. If I say the name of the array, I'm implying the address to the first element. Cool. So here I want to create my fake array using only pointer notation. So first of all, I have to create a pointer. So int ptr. Like that. So this is a pointer, and what shall I do now? So this is a pointer to an integer, essentially like array. Now the key difference that it's immediate is that when you use this array notation, you are allocating in the stack some memory, right? You are allocating essentially 10 per 4, so you're allocating 40 bytes. This is an object of 40 bytes. This is not happening with a pointer, right? I have a pointer that is pointing to an integer, a random integer. So we don't have allocation, but we can have a trick to do that. We have a function indeed which is called alloca. Not a lot used because it is not suggested, but it exists. So the alloca macro allocates bytes of space in the stack. So you see, that's the key difference between malloc and alloca. We are in the stack. We are allocating in the stack. So we have this function that is able to allocate some space in the stack, essentially like an array, right? So now I can do something like that. I can do alloca. Of course, I have to include my standard library. I call alloca of what? Size of int per 10, okay? So alloca is gonna allocate in the stack 40 bytes, essentially the same thing that is happening here. Cool. So now I can say at ptr plus 0 is equal to 42, as well as some other examples. I can say at ptr plus 1 and at ptr plus 2 is equal to another number, 1337. And minus 21. Let's do the same with the array notation that you know pretty well. We have array 0 equal 42. I'm gonna copy this and paste. And then I do array in position 1 is equal to the same value, as well as for the last. Okay, we have something which is almost equal. Do you agree? Now let's print the values. So I do a loop for int I equals 0, e minor than 10, and then plus plus I. We are gonna print the value which is in the relative position. Okay, so we have array in position I. We do the same essentially for my fake array, only I use pointer notation. So at ptr plus I. Okay, of course I have only 3 numbers. The other numbers are gonna be random, but we don't care. Let's try to launch this code. So I'm gonna compile with all the flags, and as you can see immediately I have this warning. Then it's telling me alloca is discouraged. There is no way to check for failure and some other details, but we don't care. This is just a sample to understand principles. So I'm gonna compile normally and then I just launch. You see, it allegedly works. Now let's make the code more clear. In the middle here, I'm gonna put some spaces to make the code more readable. Okay, put string, 2 spaces, plus the one from put string is gonna be 3. Okay, so I'm gonna compile normally and then I'm gonna launch. So here it comes. I have my first array and then I have my second array. So as you can see immediately, the first 3 numbers are the ones, essentially like the real one. Cool. Now it is kinda the same. Let's try to find some differences here. First of all, I would like to increase directly PTR. PTR is just a simple pointer, a simple variable that I can change. So I'm gonna do directly PTR plus plus. I can remove the braces. Of course, they are not necessary. So I remain with this expression here. Of course, I have these operators. The plus plus is gonna be performed before because I have associativity that comes from right to left when we have unary operators, but nonetheless. Here I want to do the same. So I'm gonna do not array I. I would like to try to increment this and the reference because we know that the name, the identifier of the array is equal to the pointer to the first element. We just saw that. Let's try. So I'm going to compile and immediately I get this mistake. Cannot increment value of type array of integer of 10 elements. So I cannot increase directly the value of this identifier. Strange, given that this is just a pointer, right? So this is one key difference between these two. I cannot do that. On the contrary, I can do very easily, right, with pointers. Let's try to compile and launch. As you can see, it works correctly, no problem. So to make it more equal, I'm gonna try to do something. I'm gonna say this is a pointer, but this is a constant, okay? So here is written, this is a pointer constant to an integer, okay? So now if I try to compile, I'll get almost a similar thing, right? Because I have the constant qualified type. So basically I cannot perform pointer arithmetic directly on the pointer itself. Basically I cannot change the value of the pointer. Okay, so we managed to get a similar behavior if you want. Indeed, when you search online, for example, is an array just a constant pointer, you will find many people that will argue, yeah, essentially an array is almost like a constant pointer. It is not the same, but you can consider an array like a constant pointer. Of course, this is not the case, right? If you want to go deep, they are not the same thing, but search by yourself, is an array a constant pointer? And you will find some good information. Now, people is telling that an array is just a constant pointer because of this. You have this similarity. And indeed, that's legit. In your mind, you can consider the name of an array just a constant pointer. But now I will show you that this is not quite the case. So let's start from the beginning and let's watch all the similarities between the two. First of all, I'm gonna printf the address of the array and I do %p. Okay, so I use the array identifier, which is array. That you know that is basically a pointer to the first element, so I can do that. Okay, here I put this time my pointer. I compile, and as you can see, they're pretty close, right? They are equal 7930, 7900. They both live in the stack. Okay, they point in the stack. Okay, so this is the first point. This array and all these elements are living inside the stack. First thing which is equal in the stack. Okay, as well here in the stack. The other thing that you just saw is that we cannot increase r, as well as we cannot increase this constant pointer. So cannot increase. So this is the same. Okay, we have two things which are equal. Now let's find something which is not equal. And here we're gonna do size of operator. I'm gonna use the size of operator, and I'm gonna printf %zoo the size of array. So the size of r. I'm gonna do the same here for my pointer. So size of ptr. So let's try to launch this time the code, and let's watch if it is exactly the same. I'm gonna compile. Opa, here I get something different. Here I get 40 and here I get 8. So this is a big difference. What is happening? Well, when I call here the size of on my constant pointer, what am I getting? Well, I'm getting the size of a pointer that you know by now that this is 8 bytes, right? Depending on the machine, in my machine is 8 bytes. On the contrary, when I call here size of on the array, what is happening? Well, I am getting the size of the entire array. I'm not getting the size of a pointer. You see the catch? I'm getting size of array, which is 10 per 4, because this is the size of all the objects. So I have an object in memory, which is 40 bytes. Here I have a pointer. I don't have an object of 40 bytes. I have a pointer, and in every location in my stack, I'm gonna put manually all these values. You see, this is a big difference already. Now let's try with another operator, which is the ampersand operator. So I'm gonna copy this. I'm gonna print a pointer to the address of array. And then just beneath, I'm gonna do a pointer to array. So I want to do the same operation with my fake array. So using the ampersand, I'm gonna do printf %p, so address of ptr, and as well ptr by himself. What is going to happen here, my friend? Let's watch carefully. Compile, and then just launch. You see something peculiar. With the array, I get the same address, both when I use the ampersand here and when I don't use it. These are the same pointer, the same address, but they are of different type. Here I have a pointer to array of type. In this case, I have a pointer to an array of 10 integers. And here I just have a normal pointer to an integer. So they, of course, point to the same memory location, but they have a different type. What does it mean? Well, it means that if I perform pointer arithmetic with this, I get a different result respecting to this one. Let's try. So I'm gonna do that, pointer arithmetic. And this time, as you can see, I'm doing pointer arithmetic to this pointer and to this pointer, which you just saw, they are the same. Let's try out. I'm gonna compile and launch. Look at that, my friend. What do you see? They, of course, point out the same address, but when I perform a +1, I don't advance equally. Here, I only advance 4 position. On the contrary, here, I advance much more. Indeed, here, I jumped 1 array position. This is, of course, hexadecimal notation, so pay attention to that. So when I use the ampersand on the name of the array, I get a pointer which is of a different type respecting to this name of the array alone. So I get a different pointer arithmetic. You recall from the previous videos, I told you that the data type of the pointer is going to imply the way by which we read data in the respective memory pointed and the pointer arithmetic itself. This is what is happening. On the contrary, here, what do I have? I have a pointer to a pointer, and here I have a simple pointer. So if I do the same trick, so I'm going to do this and that, and here I'm going to say +1, and here +1. What is going to happen? Compile. So I get those results. So this is the address of the pointer, this is the pointer itself, this is the address of the pointer +1, and this is the pointer +1. Of course, this is not very well written. I should have written the output better, but you get the point, I guess. This is the address of the pointer. When I say pointer +1, I jump here. I jump 8 because a pointer is 8 bytes. Here on the contrary, I say pointer +1, I jump 4 because an integer is 4 bytes. So let's not dig too much into this technical stuff, which is not easy. And let's understand the overall idea. So I have these two objects, an array and a fake quote-unquote array that I created. They are basically the same. They both allocate memory in the stack. This is happening because this is an array, you know how it works. You have a location in memory. Here, on the contrary, I perform myself the allocation using this function, which is not suggested, but that's how it works. So it's gonna allocate 40 bytes in the stack. This is a constant pointer to an integer, almost like this. So both are in the stack. Okay. I cannot increase array as well as I cannot increase PTR because this is a constant. The difference is that when I use size off, I'm going to get the size of all the object, of all the array. When I use size off on my pointer, I get the size of my pointer because this is just a pointer. When I use the ampersand, I get the address of the pointer. On the contrary, when I use the ampersand on an array, I get the address of the array data type, so I get a pointer of a specific data type. In this case, I get an address to an array int 10. So we get these things which are not equal. And now let's understand why. Let's understand what is going on. We have this array pointer duality. The best analogy that comes to my mind is the wave particle duality, right, of quantum mechanics. We don't actually know if a particle is a wave or a particle because sometimes it behaves like a particle, sometimes it behaves like a wave, and that's all confusing. So in the same way, we have arrays and pointers. Sometimes they are arrays when I use the size of operator, and sometimes they are just pointers when I just dereference the first element. It is just a pointer at the end of the day. So this is confusing. Indeed, my friend, there is this phenomenon which is called array decay, in which the array basically is a pointer, okay? You can perceive the array as a pointer. And this is the message I want to convey to you. We don't want to get bogged down into technical details. We just want to write code. So my suggestion to you is that when you work with an array identifier, much probably that is just a pointer to the first element, okay? Here I just created this stupid model, standard model of arrays and pointers, by which we have an array that always decays into a pointer to the first element, but not in all situations. For example, when we want to increment the name of the array, you just saw we cannot do that. We cannot increase the name of an array. When we use the ampersand operator with an array, we get the address of the array data type. We don't get an address of a pointer. Okay, we get an address that has a specific type that is the type of the array, int array 10 in the case before. So it's kind of tricky, right? This array decaying is kind of a tricky beast to master. Now, let's see what is written in the C standard. So except when I use the size of operand or the ampersand operand or a string literal to initialize an array, an expression that has type array of type, we have a conversion to an expression of pointer to type. So the array is decaying into a pointer that points to the initial element of the array. Okay, so this is essentially what is happening. Keep in mind the stupid model I've created because I think it's fairly useful. It gives you the idea of what is going on. So let's write together a little piece of code so we can understand better this idea. So as usual, my main function at the top, and then I create an array of 10 elements to integer, like always. So I know that every time the array identifier is going to decay into a pointer to the first element, but not always. Like if I do printf, you saw before, zoo, size of v, we don't have a decay. Here the value is going to be 40 and not 8, right? But if I do something like that, I do ptr, and then I do ptr is equal to v. What is happening here? Well, I'm not assigning an array to the pointer. I'm assigning a pointer to the first element, you see? So here, if I say v in position 0 is equal to 42, here I can see that value just with the printf, and I say at ptr. This is exactly the same, right? So I'm going to run. As you can see, this is the size of the object, and this is the element in the first position, accessed through the pointer. See, because here I have a decay. Here I don't have a decay. Why? Because I'm using the size of operator. So the decay as well doesn't hold if I'm using the ampersand operator, you saw before. So I just remove this. Here I'm getting the address of the array, which is equal to the pointer to the first element, but is of a different type. This is the key difference. And basically that's it. I don't want to give you too many details because at a certain point you don't need to stress out too much. When you work with arrays, you have an object allocated in the stack, and this is different from a pointer. An array is not a pointer. The trick is that very often an array decays into a pointer. So we can basically consider an array like a pointer. The thing is so intertwined that basically I can use pointer notation like that to access elements inside my array. I want the object at position v plus 1. Okay, so I'm gonna do v1 is equal to 42. But I access with pointer notation. Why? Well, because this is a pointer, my friend. This is a pointer. so I'm gonna run. That's the same, you see? So what is at the end of the day the difference between array accessing in this fashion or in this fashion like that? Well, there is no difference indeed. They are the same. The square bracket notation at the end of the day is just syntactic sugar. It is easier to perceive what is going on with this way of typing, but underneath the hood, what is happening is that we get the reference of a pointer, you see? Coming back to a previous principle that I explained in a previous video, we have C, which is consistent and regular in its approach to address arithmetic, right? Its integration of pointers, arrays, and address arithmetic is one of the strengths of the language. That's why pointer arithmetics works the way it works. It's basically array indexing, right? When I increase by 1 and pointer to a short, I'm increasing by 2 positions because I want to access the following short, the following object. So when the compiler sees this v square bracket 1, what is happening is that it converts this to that, okay, plus 1. So we can do something really murky now. We can do that. We can do printf, the same, but this time I'm gonna do 1 in position v. Oh my god. Do you think it's gonna work? 1 in position v. This doesn't make any sense, but let's try. Well, you see, it works as well, because what is the thing here? At the end of the day, the compiler is gonna translate this into this. So it's the same, right? At the end of the day, this is commutative. This is the same thing. So we can do really strange stuff because at the end we have the referencing of a pointer. Now let me show you some other quirks just to have fun, not to learn this stuff because it's very bad programming. But you can do printf, for example, the char in a string literal. In a string literal that it is an array of char in C. So I do hello and I take the one in position 3, or let's do the one in position 0. Let's take the h. Do you think it's gonna work? Let's run. So it's gonna give me back the h because this string literal is an array underneath the hood, and this is array indexing. But I told you that this is just like pointer dereferencing, so we can do this. Okay, let's try. I'm gonna run. As you can see, I get 2 h's the same, or I can do something like that at 2. This is gonna be so bad to see. This is gonna give me back an L, HHL, as you can see, right? Now you understood the trick, right? We don't have to go any deeper. You can do super strange stuff given the nature of reality in C. So the message I want to convey to you is that arrays are arrays and pointers are pointers. They are indeed different things. But as Drake is telling us, to Drake, that's just a pointer. End of the story. Be Drake, be cool. Because when you're working with arrays, unless you're using the size of operator or the ampersand operator or so forth, you are handling a pointer to the first element. So in your mind, you can think, okay, this is a pointer to the first element, end of the story. So now let's try to respond to some questions. And the first one is, why this array decay? Well, it's fairly simple, right? If you reach this level of the course, you know that when an object is decaying to a pointer, we have a reference to it. So let's pretend we have a very, very big array and we are passing to a function. Well, we are not passing a copy, so the function doesn't have to copy all the thing, but it just have a reference to it. So it's efficient in memory usage when passing an array to a function instead of creating copying. So when passing an array to a function, we are not creating a big copy, and this improves performance overall, right? So you see this little stupid program. I have my main. Inside my main, I'm going to declare a big array, and then I pass to foo. Foo is going to receive just a pointer, even though here I write a square bracket. This is a pointer. When I write a square bracket, I just say, hey, keep in mind that in the main I have an array and not a pointer, but they are the same. right? You can do like that or like that. So the full function is going to receive only a pointer to the array. It's not going to receive a copy of that. It's not going to copy all the array in its local frame. Of course, here I can write in these two fashions. It's totally the same. So I compile and launch. You see? Cool. So having this decay is going to improve your memory usage. This is flexible, of course, because every array has a specific data type. I can have, in the examples of before, I have array int 10, array int 15, array double 30, you know? So for every array, I would need an ad hoc function. I don't want to have many functions that are dealing with specific array types. I have an array that is decaying to a pointer, so a pointer is a pointer. So I can have a generic function that is able to perform its operation to every kind of array. The bad part is that I have loss of size information. Basically, when I pass an array to a function, I don't know anymore how big is this array. So I need all the time to bring with me an anchor value, which is the size, right? Every time I call a function, I have this cumbersome size that I need to pass, or I can use a sentinel value. For example, interleaved inside the values in my array, I can have a value, for example, a negative value, given that my array has only positive values, that will apply as a sentinel value. But you have to engineer a way to communicate to the call function that this is an array of a specific type. What is the deal here? Let's try with the code to explain why this is important. You see here, I have my little code with symbolic constant with a value 100, size symbolic constant. So I create my array, which has 100 elements. Then I go to populate my array with random values. Then I want to call my function, which is print elements, and I give as an input my array v. Okay. Now print elements would like to print the values inside my array, all the values, but it doesn't know how. You see, because I have my for loop, which has the exit condition when I is minor than what, given that v here is only a pointer. You see the catch. So here I need to pass the size. So we are gonna pass size, and here I'm gonna put int size. Okay. So here I do is minor than size. Now we can work. You see, to make it crystal clear. If I do printf zoo of v, here I'm gonna get like that, size of v. Here I'm gonna get 8 and not the size 100. So let's run this code and let's try to see what is going on. 14 anchor size, and here I have all the random values which are inside my array. The first one, of course, is the value 8, which is the size of the pointer received. Here there is a little mistake. There shouldn't be size of int. So let's try to launch again. And then here I want to tweak a little bit the code to make it more readable. Let's do modulo 101. So I have numbers ranging from 0 to 100. Compile, launch. Okay, now I have all the numbers that I want. And here at the beginning I have my 8, which is the size of the pointer. Basically the name of the array that at this level has decayed into a pointer. So I guess you understand what is going on. Okay, all the times I need to bring with me this size value. Otherwise, the call function doesn't really know how big the array is. So like all the things, we have pros and cons, trade-offs. Now, the question that you just saw before, so I'm not going to repeat, why array index 5 is equal to 5 index array? Because at the end of the day, we are dereferencing a pointer. So very shortly, the C standard defines the square bracket operator like the referencing, right? So array and index expression is equal to pointer and offset. That's totally the same. So if I say array 5, I'm saying at array plus 5. And if I say 5 array, I'm saying at 5 plus arrays. So you see, I'm just inverting the values. And of course, this is commutative, and that's no problem at all. But you understand this idea, right? Okay, we have finished with this duality array and pointers. I tried to explain as the best as I can, but I understand that this is tricky. Keep in mind this idea. An array is an array, but most probably it's going to decay into a pointer to its first element. So you have this standard model of array and pointers, by which an array is just a pointer in your mind. And believe me, every time I write code, I I basically forget that an array is an array at the end of the day. So for any practical purpose, they are the same. Now, pedantically speaking, you understand that they are not.